Bismillahirrahmanirrahim. My name is Muhammad Munir, roll number 21T05. In this video, I want to discuss about Lab 8 of Digital Signal Processing. Our instructor is Dr. Muhammad Jamil. So, moving toward Lab 8, lab objective of this lab is to implement an analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design method. So, moving toward task 1, which is about question that is define filter. So, filter is the context of DSP refer to a system or algorithm that modify the characteristics of digital signal. Now moving toward question number 2, that is types of filter. So there are various types of filter, that is low pass filter, high pass filter, band pass filter, band stop filter, which is also known as notch filter, and last one is all pass filter. Now moving toward next question, that is what are the time domain parameters for a filter. So first time domain parameter is step response. So step response, we need step response for a ideal filter because a good step response indicate that filter settles quickly and smoothly to its final steady state without significant overshoot or oscillations. Next is overshoot. A low or negligible overshoot is desirable as indicates that filter output closely matches the desired response without significant deviation or transient effect. Last one is a linear phase. Linear phase is considered beneficial as it ensures that all frequency components of input signal experience the same phase shift, preserving the signal waveform and avoiding phase distortion. So moving to our next question, that is what are the frequency domain parameters for a filter, that is role of ripple in pass band, and last one is poor stop band attenuation. Last question, that is discuss the role of low pass filter for filter designing. So there are various roles, we discuss few of them, that is first one is selecting desired frequencies while blocking higher frequencies, preventing aliasing in DSP. Now moving to our task number 2, that is plot the signal in time and frequency domain along with its magnitude response. So we have given signal that is x of 1 to 40 is equal to 0. So the source code for the signal is, first of all we define the signal x, that is x 0s 1 to 40, that plot the signal in time domain. We use figure command, then use subplot for plotting different plots in one fig, that use temp command, then give title, that is signal in time domain, then using x label and y label, then compute the Fourier transform, that is x is equal to f of t, then compute the magnitude response, then plot the magnitude response, that we use subplot, stem command, give title, x label and y label. Finally we plot the signal in frequency domain, so again using subplot, using stem, that give title, then give x label and then give y label. The output is like this, we have signal in time domain, magnitude response, and then signal in frequency domain. Another signal that we have given, that is 41 to 120, that is one source code, same like as previous one, that first of all we define signal, then plot the signal in time domain, then compute the Fourier transform, then compute the magnitude response, then plot the magnitude response, then plot the signal in frequency domain. And then another signal that we given, that is 121 to 161 is equal to 0. We define the signal, then we plot the signal in time domain, then we compute the Fourier transform, then compute the magnitude response, then plot the magnitude response, and then plot the signal in frequency domain. As a result, we get an output that is signal in time domain, magnitude response, and then signal in frequency domain. Moving to our next signal, same like as previous one, we have a signal, we define the signal, then we add noise, that is x noise is equal to x plus 0.5 into radian size of x, then plot the noisy signal. We use various commands for this, then we compute the Fourier transform, then compute the magnitude response, then plot the magnitude response of that noisy signal in frequency domain, then plot the noisy signal in FFT plot. As a result, we get a noisy signal in time domain, magnitude response of that noisy signal, and then noisy signal in frequency domain. Then we give another signal, same like as previous one. We define the signal, add noise to x, then we define the moving average filter coefficients, then apply the moving average filter coefficient to x noise, then plot the filtered signal, then we compute the Fourier transform in the filter signal, magnitude response of that filter signal, plot the magnitude response of filter signal, then we plot the magnitude signal in the frequency domain. As a result, we get a filtered signal in time domain, magnitude response, and filter signal in frequency domain. Then the questions which we ask that apply t-type filter symmetrically around moving average filter on signal x noise and observe the time and frequency domain parameter. For this, we define the signal, then add noise, then define the moving average filter coefficients, then apply the moving average filter, then plot the filter signal in time domain, then compute the Fourier transform of filter signal, then compute the magnitude response, then plot the magnitude response of the filtered signal in frequency domain, then we plot the filtered signal in frequency domain. As a result, we got an output that is filter signal time domain, magnitude response of that filter signal, and then filter signal in frequency domain. Then other question is that apply 11 tap around moving average filter on x noise and observe the time and frequency domain parameters. Same like previous one, we define a signal, then we define the moving average, then apply the moving average filter, then plot the filtered signal, then compute the Fourier transform, then compute the magnitude response, then plot the magnitude response in frequency domain, then plot the filtered signal. As a result, we get an output filter signal in time domain, magnitude response, and filter signal in frequency domain. Then we apply 25 tap around the moving average filter and observe the time and frequency domain parameters. So the source code of this 25 tab filters is, we define the signal at noise, then we define the filter length that is 25, then apply the moving filter, then plot the filter signal in time domain, then compute the FFT, then compute the magnitude response, then plot the magnitude response, then plot the filter signal in FFT. So we get an output that is filtered signal in time domain, magnitude response, filter signal in frequency domain. Now moving to our task number 3, that we ask the question that repeat example 7.2 for 17 tap coefficients. The source code that we define constants, that is n, that is 17, that is number of types. Then we define carrier frequency, that is 800, the sampling frequency is 8000. Then we normalize cutoff frequency by using formula, then calculate the filter coefficients, then display the filter coefficient, then determine the transfer function, then convert the transfer function to a symbolic form, then display the transfer function, then determine the difference equation and display the difference equation by using DISP command, then compute and plot the magnitude frequency response. Then finally we plot the signal, then mark specific frequencies. As a result we get an output that is filter coefficients, transfer function and difference equation. Also we get an plot of magnitude frequency response. Another question is that repeat that same example 7.2 for 51 tab coefficients. Same like we get defined constants FC, FS, then normalized cutoff frequency, then calculate the filter coefficient, then display that filter coefficient, then determine the transfer function, that then transfer function convert to symbolic form, then display the transfer function, that determine the difference equation, then display the difference equation, then plot the magnitude frequency response, then plot the signal, then mark the specific frequencies. As a result we get it filter coefficients and transfer function and difference equation. Also get we get magnitude frequency response. Same like we repeat that example for 51 tab coefficients. For that we define constants FC, FS, calculate the normalized frequency, then calculate the filter coefficient, then display the filter coefficient, then determine the transfer function, then convert the transfer function to symbolic form, then display the transfer function in symbolic form, then determine the difference equation, then display the difference equation, then compute and plot the magnitude frequency response. Then we get plotting more specific frequencies and observe the frequency domain parameters. As a result we get filter coefficients and we get a plot of magnitude frequency response. Now the part B of task 3 is that apply the filters made in part A to the signal X signal. Observe the changes for that signal in time and frequency domain while varying the number of coefficients of filter. Source code that we define original signal generation, that is sampling frequency, define time, then define three signals, that is x1, x2 and x3. Then we add up these signals and then plot the original signal in time domain, then plot the original signal in frequency domain. Then design and apply FIR filters with varying number of coefficients. Then apply filter to signal X, then plot the filter signal in time domain and then plot same signal in frequency domain. As a result we get original signal in time domain, original signal in frequency domain, then filter signal with 17 coefficient in time domain, with 17 filter in frequency domain. Then moving to a task 4, the part A of that task, that is repeat example 7.3 with 7 tab or 17 tabs. So first of all we defined constant, that is number of tab, that is 17, sampling frequency, that is 8000. Then we define low cutoff frequency and upper cutoff frequency in hertz, then normalize the frequency, calculate the bandpass filter, display the filter coefficient, then display the transfer function, then convert the transfer function to symbolic form, then display the transfer function in symbolic form, then plot the frequency response. Then again we get a plotting. As a result we get a frequency response of 17 tabs, that is like this. So now moving toward part B of that task 4, that is apply filter made in part A to the signal. Observe the changes in signal in time or frequency domain while varying the number of coefficients of the filter. So source code, we define original signal, that is sampling frequency, time. We have three signals, then we add up three signals, then plot the original signal, then we plot original signal in time domain. Then we define filter coefficient for 5 tab, 9 tab, 17 tabs. For filters we start a for loop, then apply filter to a signal x, then plot filter signal in time domain and plots filter signal in frequency domain. As a result, we get original signal in time domain, original signal in frequency domain, filter signal in 5 tab FIR bandpass filter in time domain, same FIR bandpass filter in frequency domain. So these are tasks are of lab 8. Thank you so much for watching my video. Allah Hafiz.